Okay, class, we're about to start section 2.5, and as we see in our syllabus, we're to do page 165 and page 169. Now, 2.5, on page 165, we have lesson 2.5, sit back and watch your money grow. Our learning objectives would be to illustrate exponential growth with a graph, solve problems using graphs representing exponential growth and decay. Identify the significance of the parameters in the exponential equation and find and interpret exponential models. Okay, now we go down here to number 1. It says, describe the difference between linear and exponential growth based on what we know from earlier in the course. Linear growth is steady. You keep adding the same thing I should say value. The same value to get the next one. Exponential growth grows faster and faster. You keep multiplying each value by the same value to get the next one. What do you think is meant by the relative change in a quantity? How do you compute relative change? Referring to the topic of relative difference in lesson 1.6 should help. It is the size of the change expressed as a fraction or a percentage of the original size. To calculate it, you divide the amount of the change by the original amount. Okay, now we'll go over to page 166. Now, it says, if you're like a lot of people, you go on a spending spree if you won $10,000 on a game show. But what if you decided to invest that money rather than spend it? And what if you were patient enough to let it grow for 40 years in a savings account? Let's take a look. Make sure that you answer every question with a complete sentence. Number 3. For each value in the table after the initial investment, divide the amount by the value of the account the previous year. What do you notice? Now, we're not going to physically write this out. We're going to do this in a calculator. So we would take 10,700 and divide it by 10,000. That gives us 1.07. Then we would take 11,449 and divide it by 10,700. And that would still give us 1.07. We could just try the next number. I'm not going to go through all of them, but we had 12,250.43 divided by 11,449, and that still gives us 1.07. So we could safely assume that all of these are multiplied by 1.07. So all of these have the same multiplier, 1.07. Okay, now, so what do we notice? Every time we get 1.07, and then some of them would be estimates to get the 1.07, so we'll put or something very close. Okay, now it says, what does your result in question 3 say about the type of growth this account exhibits? Every value is multiplied. So this implies that it is exponential growth by 1.07. Okay, now we move on. It says find the relative change in value for each year in the table compared to the previous year. What can you conclude? Okay, so basically what they're asking us to do when they say they want us the relative change, we would take like year 1, we would take year 1 minus year 0, year 2 minus year 1, and so on. And so when we subtract this, we would have 10,700 minus 10,000, which is equal to, well, actually it's supposed to be divided by 10,000 as well. Because remember, it's new minus original divided by the original. So it'd be 0.07. And then we would do the same thing, 11,449 minus 10,700 divided by 10,700. It still would give us 0.07 when we put it in our calculator. And then we would take the 12,250.43 minus 11,449 divided by 11,449. It would still give us 0.07. Next, we would take the 13,107.96 minus 12,250.43 divided by the 12,250.43, and it still would give us 0.07 once you put it in your calculator. Now, we'll move on now to the 14,025.52 minus 13,107.96 divided by the 13,107.96, and it still would give us 0.07. So next we would take the 15,007.30 minus 14,025.52 divided by the 14,025.52, and that still would give us 0.07. Then we would take the 16,057.81 minus the 15,007.30 all over 15,007.30, and that'll give us 0.07. Now, when you all physically put this in all of your calculators, there's going to be some instances where it may be 0.071 or 0.072 or something like that. But if we all round them to 2 decimal places, then it will give us these values here. So the account is growing by 7% each year. So that 1.07 that we got earlier that we're multiplying by, in real terms, the money is growing by 7%. Okay, now we move on to the next page. Get in problem 6 here. Now it says, here's a quick summary of what we learned on page 166. The account starts at $10,000 and grows by 7% each year. Mathematically, this is accomplished by multiplying the previous year's amount by 1.07. So after 1 year, the amount is 10,000 times 1.07. After 2 years, it's 10,000 times 1.07 times 1.07, and so on. The result is that an equation that describes the value after X years is, now it'll be y equals 10,000 times the parenthesis 1.07 to the X power to indicate the years. And now we know why this type of growth is called exponential growth. We can use the exponent to represent the repeated multiplications that we get when a quantity is multiplied by the same amount over and over. Verify that the above equation generates the account values in the table. Ideally, you would use either the table feature on a graphing calculator or a spreadsheet, but in any case, make sure you describe how you got your values. Okay, so this is what we would do. We turn on our calculator, go to y equals, and we would type in this equation. We have 10,000, parenthesis, 1.07, close the parenthesis, hit the exponent key, and hit X. Now we just go to second, and then graph, and we look here at the table. Now, if we go back here, we look here at the table. This is our table. This is our calculator. Now, if you look here at the table, we got 10,000. We have 10,700. We have 11,449. Now, if you notice here, we have 12,250.43, but we only had 12,250 here. So we could go down here and go to the right, and you notice we have our 43 here. We go down, it'll be 13,107 point, and we know we only had 2 digits behind the decimal with our money system. And then it'll be so on, up until we get to the 7th year. Now, it can't go on forever. Now, it says they want us to describe what we did. Okay. You say, I created a table on my graphing calculator. And all values match when you round to 2 decimal places. Okay, now we'll move on to problem number 7. It says, look back at the graph that illustrates the value of the account. Trace along the graph slowly from left to right and describe what the change in steepness of the graph tells you about how the value is growing. Okay, so now, if you look here at this graph, this was the graph we initially had. And if you notice how the steepness is going here, so we need to describe that. So, the graph does not start off very steep. So the account is growing slowly. As you move to the right, the graph gets steeper, which means the account is growing faster every year. Okay, now, again, just looking back here at the graph, you notice here, as the account starts growing, it's growing much, much faster. So in 40 years, you have close to $160,000, which is not bad. All right, now we come here to number 8. It says, how much interest will you earn from 0 to 5 years into the investment? This will be the difference in the value after 5 years in the initial investment. First, estimate the answer by looking at the graph, then perform a calculation using the table provided. Okay, so if we go from 0 to 5 years, let's go back here. If we go from 0 to 5 years, 0 to 5 years would be about in the middle here. So if you look here from 0 to 5 years, it's going to be about, maybe give or take, about $5,000. Okay, now, so on the graph, it appears to be about $5,000. It is actually $4,025.52 using the table. So if we go here to the table, 5 years is at $14,025.52. So we would just subtract these two values. The $14,025.52 minus $10,000. So I could write it here, $14,025.52 minus $10,000. So that'll give us $4,025.52. All right, number 9. It says, how much interest will you earn between years 35 and 40? Again, estimate from the graph first and use the equation you wrote to get an exact value. Okay, so this is what we could do. We go here to the graph. They said between years 35 and 40. That looks to be about 40,000 between years 35 and 40. As year 35 is about 120. Year 40 is 160, so that's about $40,000. So we could say on the graph, it looks like $40,000. Now they asked us to use the formula. Our formula is y is equal to 10,000 times 1.07 to the x. So we'll do y is equal to 10,000 times 1.07 to the 35th power. And that gives us $106,765.81. And then we would take this formula again. And this time we would take 10,000 times 1.07 to the 40th power. And that would give us $149,744.81. So now we need to subtract both. If we subtract both, so we could bring this over here. That would give us $42,978.77. So this is the actual. $42,978.77. Okay, now for number 10, it says describe what you can learn from comparing the answers to questions 8 and 9. Also describe how that fits in with your answer to question 7. Okay, so from 0 to 5 years, the interest is $4,025.52. From 35 to 40 years, the interest is $42,978.77. So basically, it pays to leave your money in the account for a long time, because you make a lot more interest in later years. Okay, now we come to the last problem of this first portion of section 2.5. It says, my all-time favorite TV show was Highlander. It featured a race of immortals whose destiny is to battle each other over hundreds and in sometimes thousands of years. The fact that most of them appear to be fabulously wealthy strikes a lot of people as hokey, but based on what we've learned in this lesson, it actually makes a great deal of sense. Suppose that you could travel back in time to the year 1700 and invest the very modest sum of $10. Suppose further that the investment draws a very modest return of just 5% each year. Comparing to the equation at the top of page 167, write an equation that would describe the value of this account after X years. So it'll be Y is equal to 10 times 1.05 to the X power. Now, if we go to, this is 2019, and we'll go back to 1700. That'll be 319 years, which would be our X value. So we have Y is equal to 10 times 1.05 to the 319th power. So let me put that in this calculator. So that would give us, let's see, that would give us $57,462,749.61 in 2019. Now that's a nice amount of money, but it took you 319 years to acquire it. So now what we're going to do, we are going to move on to the second portion of 2.5, which starts on page 169. And it'll be the bottom of page 169. It says, we've now studied exponential growth a couple of different times in this unit, but there's a flip side to exponential growth known as exponential decay. The thing that distinguishes exponential growth is that the growth starts off relatively slowly, then speeds up dramatically as time passes. Let's see how exponential decay compares. Coffee is a popular morning drink because the caffeine it contains acts as a temporary stimulant. Once the caffeine gets into your system, the amount dissipates exponentially, assuming that you don't add more, of course. Answer every question except for 2 and 6 with a full sentence. Okay, so now we look at this chart here. Now we go to page 170. It says, if you're the coffee drinker, represented by the table and graph, how much caffeine was initially in your system? We go here, the initial amount in your system was 180 milligrams. So 180 milligrams was initially in the coffee drinkers system. Okay, now it says find the relative change in caffeine for each 1 hour period listed in the table below. Round to the nearest 4%. Okay, class, I had to take a little time out to draw the table that was on page 169 since that was not provided. So now we want to get the relative change. So what we would do, it says from 0 to 1 year. So we would take the estimated amount minus the actual, and then we would divide it by the actual, which would be 180. So this would be a negative 0.2. Now we go from year 1 to 2, so it'd be 115.2 minus 144, and then divide that by 144, and that would give us still negative 0.2. Now we go from 2 to 3, that'd be 92.2 minus 115.2, and then we would divide that by the 115.2. And if we round this to 2 decimal places, it would still give us a negative 0.2. So all the rest is a negative 0.2, as you can see, whether it be exact or rounded value. Now, one thing I do want to show you in this calculator is how come I always got the answer first, then divide it. Because if we would have did this from, let's go back from 0 to 1, it was 144 minus 180, and it was supposed to be divided by 180. If you do it like this, you're going to get a radically different answer. That is why when you subtract it out, you get the answer and then divide, and then you will get your correct answer. So now they ask us to round to the nearest 4%. So what we have to do here, since this is a decimal, we're going to have to write this as a percent. So this would be a negative 20%. So it all went down by a negative 20%. Okay. So now it says complete the important statement about exponential change. A quantity, the relative change and that quantity is positive or negative. Looking at the graph of the caffeine remaining in your system, describe what exponential decay looks like compared to exponential growth. It's basically the opposite of exponential growth. And that, as time goes on, it decays faster and starts off at the higher value. What's the multiplication factor that you need to multiply by a previous hour's amount to get the next hour's amount? Okay, so basically if we go back here to the coffee example, well, we can actually go up here to our relative change. If you notice, it's going down by 20%. So our hint tells us if it's 10% of something goes, if 10% of something goes away each hour, 90% remains. So 20% is going away every hour. So that means 80% remains. So the multiplication factor would be 80%. That would be your multiplication factor. So that would denote that 20% has went away. Now, we move on to page 171. It says, use your answer to question 5 to write an equation of the form y equals expression, where the expression describes the amount of caffeine left in your system after X hours. Your answer to question 11 in the class portion is a good place to look if you need help. Now, first of all, we know is y is equal to, now according to our table here with the caffeine, our initial amount is 180. So remember, our initial amount is always our y-intercept. So it'll be y equals 180. And then when we did problem number 5, we see that what we're going to multiply by is 80% or 0.80. So we could put in 0.80, and then we would know it would be taken to the x power. So this is the equation that we would need to signify the rate at which that the caffeine is going out of your system. Okay, number 7. It says use a graphing calculator to verify that the equation you wrote in question 6 gives you the values in the table and the given graph. Describe your results. Okay, so we're going to put this equation in our y equals. We will have 180 times the parenthesis of 0.80 to the x power. And then we will go to the table. Now, we're going to compare this. So we go up here to 0. 0 is 180. 1 is 144. 2 is 115.2. 3 is 92.16. We round to 1 decimal place. It'll be 92.2. Then here with the 73, round to 1 decimal place, 73.7. And then so on. And it all actually works out. So now, so basically, the results are the same as the table given on page 169.